All right, line A4, learning task 3, we're going to take a look at describing series RLC circuits. And by RLC, we mean circuits that may contain resistance, inductance, and capacitance. Up until now, we've talked about the fact that inductance and capacitance are two sides of the same coin, that they're just opposites. You know, they have canceling out effects, but we haven't really seen how they actually go and cancel each other out. This is now where we're going to get into using the effects of inductance to cancel capacitance or capacitance to go and cancel inductance. The circuits that we're going to be looking at are all going to be based around something like this. Now, the order of components will make no difference. Whether we go, inductor, capacitor, resistor, we could go inductor, resistor, cap, whatever it would be, absolutely no difference whatsoever made by the order that they're going to be in. What is going to be critical, though, is the fact that they are all going to go and see the same current that is going to go and travel through the resistance, then through the capacitance, then through the inductance, or whatever order it is that we've got these components laid out in. So we've got a common component. We're going to use that as our reference when we start to go and graph everything. Because current is a common, we're going to put current at our x-axis. Close the arrowhead for current, so this is going to be my I that I'm going to go and have. If I take a look at my voltages that I'm going to go and drop, any sort of voltage over top of my resistance is going to go and be in phase. So this is going to be my VR that I would have over here. Just dot it like that. Then I'm going to go and have my current, or sorry, my volts from my inductor and my volts from my capacitor. Now, if I'm dealing with a inductor, the voltage leads the current, right? E, L, I, like that. So this is going to go and be my VL. And if I'm dealing with a capacitor, Eli the Iceman, ICE, like that, I'm going to go and have current that is going to go and lead the voltage. So here's my current, here would be my voltage, VC, like that. So we're going to go and use vectors that are going to be along those lines. Now I know the very last learning task that I did, I drew all my triangles in the wrong direction. That was sloppy of me. I shouldn't have done that. I should have drawn them all going in the correct direction, which is going to be for anything that is inductive, we are going to be above. Anything that is going to, I want to put an L in there actually, because I could otherwise look like current. Anything that is going to be capacitive is going to be down below the x-axis. So we'll take these values now, and now we'll start to go and place them together inside of here. When we go and take a look at the components that are inside of here, we should recognize as well that there could come a point where I could go and match my inductive triangle to my capacitive triangle. And then we're going to go and hit a special circumstance that we are going to go and call resonance. We'll deal with the resonance after we deal with just the simple utilization that we are going to have inside of here. The first thing that your binder goes through is it goes through a bunch of voltage vectors and the cancellation effect that we are going to go and have from the voltage on anything capacitive and anything that's going to be inductive when we are dealing with a series circuit. Now, do note that this is a series that we're dealing with. We can't use voltage triangles in parallel. We'll discover why later on, but it's a very much a series alone application. I see I've got my resistive voltage. I see I have got my inductive voltage. What they're doing right now is they're saying, I've got this circuit over here. Because it's a series circuit, I'm just going to step back, 3 steps over here because they don't really lay out what they're doing inside of here. But because it's a series circuit, I know that it has to satisfy Kirchhoff's voltage law, KVL, which is that the sum of all voltage drops is going to go and equal my source voltage. I'm going to go and have VS, I'm going to have VR, I'm going to have VC, and I'm going to go and have VL. Those are going to be my voltage drops, these three. That's going to be my source voltage, and they're all going to add up to the same. Now, if I'm going to add them, I have to add them vectorially. We looked at that in both inductors and capacitors separately, that we could just add them straight up because we came to values that were greater. But as soon as we put them in at the proper, 90 or 0 degrees, they totally worked out for us. We're going to do that again. That vectorial addition is really what we're seeing inside of these ones that they have over here, where they're going to go and take each of those individual vectors, VR, VL, VC, and they're going to add them tip to tail, as we've done before. So they start out at their origin. They're going to start out with the VR over here, right at the origin. And then once they draw in VR, they draw in VL. VL goes to the upper side, right? We're going into the top 90 degrees. We defined why we do that before. We draw VL there, and then we have to draw VC with its tail starting at the tip of VL and heading down in the opposite direction. Once again, we defined that before, that VC is going to be over here because my current would lead the voltage off of that one. What we get out of this is we are going to go and see a net vector, which is where we're going to go and end up at, right? By the time we add this, and take this thing back down to here, we end up at this net vector right over there, and that's going to go and define our system. Now, the order that you add these up in would not make any sort of a difference. You could add in the resistor, then the inductor, then the cap. You could add in the cap, the inductor, and then the resistor. It really would make zero difference for where we would end up at. They show just another permutation of it over here, where they go in from the resistor first, then they go to the capacitor. Once they've gone to the capacitor, then they come back from the capacitor to the inductor, and they would end up at the exact same values that they would have across each one of those. You can always, always, always add all of your vectors together at their proper degrees, and you would be able to go and get to, your total net that we would have. Once again, the easy way to deal with that is to go and put them into polar format, right? We would take anything that's going to be my volts for my resistance, and we'd put them at angle 0, because VR is going to be at angle 0. Anything that would be VL, we would have at angle 90 over here. Anything that we would have as VC, we would have at angle negative 90 over here. As long as we follow that convention of, our VL being in the positive 90, our VC being in the negative 90, we're going to have no problem whatsoever punching these things together. We do also see that our inductive triangles are going to be in the top, our capacitive are going to be in the bottom, which means that my inductive power is also going to be in the top, and my capacitive power is also going to be in the bottom over here. We're talking about VARs now at this point. VARs could also be added similar to the way that we did our voltages. We'll come back to that one there. But for our VARs, we would be able to go and add the total amount of watts that we would have for the circuit. We would then be able to take our VARs L, and then we would be able to take our VARs C back down. What you should note is really similar about this is that it is the exact same as our voltage one that we would have over here. Because once again, it's the same circuit. Therefore, it would go and have the exact same triangle shape to each one of these. Impedance vectors, right over here, can be done the same way. I can go and get an X net. Now over here, what they're showing is they're showing an X net off of this thing. They don't have directions so much so because it is an impedance, it's a scalar value, but we do go and apply directions to them for the sake of these. This one's different than the others in that they're not showing us adding in the XL and then adding in the XC in the opposite direction. They're just creating two impedances over here and then finding a net that they were going to go and have out of these ones. In reality, it should have probably been drawn the exact same as these, but using, my resistance value over here, then this one here is being my XL, and then this one here is being my XC. It would have made more sense and followed along with what they were doing in the rest of these. That's why I skipped past that one, and now we'll just kind of come back to it. What happens when we place these two into a circuit, a capacitor and an inductor, is really we're going to get a lot of good interaction between my VARs. Remember what VARs was? That was going to be that useless or that quadrature, that reactive, the wattless, whatever you wanted to describe it as, but it was a form of power where we were taking power and then sending it back, and then taking power and then sending it back. What we have inside of a circuit that has got both of them is that I'm going to have a section, this section right over here, that is going to be entertained, so to speak, by each other. In other words, my VARs L, instead of having all the VARs sent to the supply and then taken back from the supply, now I'm going to have some of them that are going to be fed from this capacitor that we are going to have over here. We get a leading and we get a lagging current, and we get leading and we get lagging VARs, and they just work to go and cancel each other out. In practicality, in the physical aspect of it, if I were to go and take a look at this, when I have current that is traveling through this, I'm going to have current traveling through this resistor. It's going to go and build electrons up over here. It's going to drive electrons away from over here. As it drives electrons away from there, it's going to go and build those lines of magnetic flux that are going to be around that inductor. And what we're going to see happening is that we're going to go and have current that we're going to be able to shuttle back and forth from these two that does not necessarily have to go through the supply. When this thing needs current to go and fill up its coulombs, it's going to be able to take it from the collapsing supply that it has over here, these lines of magnetic flux. And when this one needs current to go and build, to try and maintain that, it can take some of that from there instead of having to use all of its magnetic lines of flux. We really just see this cancellation from one to the other. Our power factor is still going to go and be based off our total amount of watts over top of VA. However, skipped ahead too far there. My power factor is going to go down as I go and start to correct stuff out. Let's just examine this circuit without the vars C inside of it. If I lost this var C, like that, all that I would have inside of this circuit would be my true watts, whatever those would be, plus my vars L, which would give me a total amount of VA that would look like that. But as soon as I have this var C inside of here, it drops my VA to a more manageable level. The hypotenuse will get shorter because this side of the triangle has gotten shorter as well. And I'll be able to go and develop a power factor off of that. You'll note that as we have more balanced vars L and vars C, that we are going to go and get to a better and better power factor. We're always looking for that power factor that's getting close to unity or towards 100% that we would have off of there. What would happen if we had these two at the exact same values? As soon as we start to bring our XL to the same point as our XC, then we would go and reach this point that would be called resonance. And you can really just actually examine the formulas for these. XL is equal to 2 pi FL, and XC is equal to 1 over top of 2 pi FC. And so what we would see out of these two formulas is that as I would have my frequency increasing, if I had frequency to a circuit, so that frequency is going to be seen by both the capacitor and the inductor. As the frequency would go up, I would see that this goes up, so my denominator goes up, which means that my XC would be going down. If that frequency is going up, my XL would be seen as going up. So I'm going to go and have an XL that's rising while my XC is dropping. And eventually, we're going to hit a point where both of these are going to be exactly equal. What we have done when we've hit that point where both of these are equal is we have hit what we refine to as being resonance. And resonance just means that there's complete cancellation. There is inductance, there is capacitance, but they're 100% getting fed back and forth during operation from each other. There will always be a little bit of an inrush when we first turn the circuit on, just to build the initial magnetic field and charge up that cap. There's no getting away from that, but once we've sent those electrons into the circuit, then it's like these two just have a game of catch. They just kind of toss the current back and forth. Oh, you need it? Here, you have it. I don't want it. Then the other one goes, oh, you need to take it. I don't need it at this point. So they pass it back and forth. What we do have, though, is we have the potential for some extremely high values of voltage that could be across those components, even those components themselves are not necessarily going to be active, are acting as voltage drops to the circuit. Let's go back to this one over here. Once again, we've got to go and take a look at Kirchhoff's law of voltage, right? Kirchhoff's law of voltage states that the sum of all voltage drops is equal to our source voltage. And so if we get to the point where we're at resonance, where VR equals my VC, VL equals my VC, what that would mean is that the net effect of their voltages would be 0, which would mean I would be dropping the full, whatever my supply is, we'll call it 120 volts, I'd be dropping that full 120 volts over top of just the resistance alone. But there is still current that is traveling through this, right? They're feeding current back and forth from one to the other, which means that since there's current going through there, they will still have voltage drops across them. What we're going to have as well is we're going to have an absolute minimum value of impedance in our circuit when we are at series resonance. And the reason for this is we're just simply at the very smallest triangle, right? If we take a look at this graph that they have over here, they show that we have got resistance in the circuit that's going to go and stay the same. All of these R's are the exact same. But as I go and take out my XL, so there's a little bit of XC that's been added in, taking it out. As I add in a bit more, take it out. As I add in a bit more, take it out. What we're seeing is that the hypotenuse is getting shorter and shorter and shorter. And my hypotenuse is ultimately the total opposition to current flow. I is equal to my Vs over top of my impedance, right? This is going to be my total I total that I have for a circuit. The source voltage divided by the impedance. As I see that my impedance is dropping, that would mean that I'm going to be at a maximum value of current, and if that maximum value of current is still going through a fairly significant XC or XL, that will mean that we will have a fairly significant amount of voltage that we will see across them. This can cause a lot of danger, where people think that they've got like a 120 volt circuit, but in reality, they're going to have some components that could be up at 500-600 volts. It can also cause danger for just explosion of fire, because if you've got some components like capacitors that have a working voltage, and you place them inside there and you take that thing to series resonance, all of a sudden the voltage that you're actually placing across that capacitor could be way higher than what it's going to be rated for. In the binders that you have there, the new and updated binders, they did have that mistake where they could not go and print the pi symbol properly. And the pi symbol, in a lot of cases, has printed out as being this not equals. So right underneath the picture that they have over here, you're going to go and find that not equal sign that's going to be dropped in there. Any place that you see that not equal sign dropped into those formulas, just replace that as a pi. And what they're doing over there is they're going through the XL and the XC, and they're going and saying that during resonant frequency, XL equals XC, they expand them out to the original 2 pi FL and 1 over top of 2 pi FC, and then they go and take that in and they go and create a new formula, which is going to be my formula for resonant frequency. We aren't going to write that out because the book obviously has it wrong with that not equal sign. The resonant frequency is going to be FR is equal to 1 over top of 2 pi. My pi over here is not working out. Eli, get off. Eli's on top of me right now. 2 pi and then root LC over here. So we take our inductance value in henries, our capacitance value in farads, and then we use this formula. 2 pi just once again indicates that we're working inside of a radian type of circuit system, and that we've got the complete system all the way around. And this is going to give me my resonant frequency. Every single circuit, if there is inductance and capacitance inside of it, is going to go and have a resonant frequency. There will only ever be a single frequency, which can be the resonant frequency for any type of circuit, and each one has to be found individually, just through the use of that formula. However, if I do have a circuit that has got inductance and capacitance, if I have got something that is going to be a variable frequency, so if we've got something where I can change that frequency, like a variable frequency drive, we would be able to change the frequency of the circuit, and we would also be able to go and hit that series resonance out of these things. When we do so, we can go and get, based upon the type of circuit, some tuned circuits. And tuning of circuits simply means we are setting our circuit up so that it's going to be not responsive, not responsive, not responsive, and then boom, all of a sudden it is going to go and respond. Most of you probably don't have a lot of experience with analog radio tuning, but old school analog radio tuning, what you would have is you'd have a knob where you'd be bringing that thing across, and it was simply one of these tuning circuits inside there. You'd hear static, 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 and then all of a sudden you would go and hit a very specific frequency that we were using for radio, and you'd be able to go and hear what was actually on that radio station because you had tuned it to that station. What happened was you continuously varied the frequency, varied the circuit that we had. Usually it was actually varying the capacitance so that you could go and achieve a high peak. And they're showing us a high peak inside of here, and they're showing that thing for a circuit that has got a low resistance and for a circuit that has got a high value of resistance. In simplified form, if I have got an antenna type of circuit, and that's where we would be picking these things up from, if I have got an antenna type of circuit, I would be able to go and have a low value of resistance, R low, and then as I would be varying this capacitance over here, I'd be taking it across, and then would all of a sudden hit this point where I'm going to be at my resonant frequency. As I lead into the resonant frequency, I'm seeing more and more signal, more and more current that's being allowed through, and then right over there, I would have my peak, And then as I move past that, this thing would go and drop back down. But you need to have low value of resistance for you to be able to go and see this sharp of a curve. If I have got a high value of resistance, something like that, then I'm going to go and have just a much smaller looking curve over there. It's all going to vary off of what we have over here. If I also have got this low value of resistance, I'm going to go and have a maximum amount of current, which means that maximum amount of current is still going to be transferring through this inductor and through this capacitor. Sorry, I said those wrong. Through this capacitor and this inductor over here. As it does so, we are still going to establish voltages. V is equal to IR, right? My volts are going to be equal to my current times my resistance, which means that they can, in some cases, have ridiculously large values of volts that are going to be across there. Once again, the way that these two react together is going to be established by something that we are going to go and call the Q. We use Q for everything inside of second year, right? We've used Q for coulombs, we've used it for the quality factor of a coil. Now we are going to go and use it for the quality factor, the Q factor of a circuit that we are going to go and have. And the Q factor of a tuning circuit is going to be a ratio of its VARs divided by the true power. VARs divided by watts, which once again is going to be very similar to what we saw for the Q factor for an inductor. If we're seeing VARs and watts, we should recognize that this is going to be a tangential relationship over here, where they can be tied together through the use of tangent, which is going to be my opposite over top of my adjacent, right? Adjacent being watts, my opposite being my VARs that I'm going to go and have here. Very, very much so, although you can get these two in a single package, where you're going to have that inductor and capacitor together, the resistance that you placed in line with that is going to make a big difference to the steepness of the curve. If I want maximum signal, I want to have minimum amount of resistance so that I'm going to be able to have maximum current at that specific frequency. We'll cover these tuned circuits a little bit later on when we go through some electronic stuff, particularly where we're going to see this, though, this series resonance being critical, is when we get to filtering in third year. You will probably have forgotten about this because, who bothers remembering anything from previous years when you come back to apprenticeship schooling, but just don't be that apprentice. Remember that when we have got a series circuit, we can tune it to very specific frequencies where it's going to go and have a low impedance to those specific frequencies, right? Obviously, whatever this frequency is, the circuit has got a very low impedance because this XL is being canceled out by this XC, leaving us only with this amount of resistance. What we will do with these is we will set these up to some of our harmonics. We'll use them for power, quality, and for filtering, where I might go and set this thing up for third order harmonics, second order harmonics, 180 hertz. We've got some really bad frequencies that are just created as multiples inside of our systems. When those things are created inside of the systems, they cause issues with like neutral overheating and with, the different ways that they cause like shred factors and things like that to just kind of get out of control. So since we don't want to have them, we want to go and provide an easy way for them to get out of the system. Anything that I create in my system, if this thing was tuned for 180 hertz, any 180 hertz harmonics that would be in the system would have a low impedance path where they could go and dissipate just as heat over top of this resistance over here. Makes it really useful. So expect to hear about those again once you get into your third year materials.